So yeah, maybe let me start with an observation which was made already in some of the talks this week, which is that so if you take the abelian free groups, so Zn and Zm, then they are elementarily equivalent if and only if they have the same rank. So that's something you can prove quite easily by observing that Zn, well, 2Zn has order 2 to the n, and that's something that you can express using a first order sentence. And so, yeah, there is this rigidity. And around 1940, Tarski asked about the analog, but for free groups. So, is the rank of a free group determined by the first order theory, or are free groups elementarily equivalent? So, is it true that Fn is elementarily equivalent to Fm for n and m? At least 2, of course, because if you take m and n smaller, I mean, F1 is Z and F0 is trivial, so it's obvious. And so this problem remained open for quite a long time, and now we know that the answer is yes, and that's a result which is due to Sela and Kharlampovich-Myasnikov. So the answer is yes. But in fact, what they prove is much stronger because they give a complete classification of the finitely generated groups with the same first order theory as Fn. And I will give you the classification in a moment. So they give a complete classification of the finitely generated groups G such that G is elementarily equivalent to F2. And you see this assumption, finite generation, is very important because, for instance, if you want to remove it and replace it by countable, it's an open problem. So really, it's only for finitely generated groups. So let me give you one of the examples of groups that are not free, that are finitely generated, and that are elementarily equivalent to a free group. So, examples. So, example number 1 is the group given by the following presentation: A1, B1, up to AG, BG, satisfying the relation which is the product of the commutators is 1. This group is not free, and it is elementarily equivalent to F2 if we assume G greater than 2. Because of course, if G is 1, then it's just Z2, and it's not possible. And if you know a bit of algebraic topology, then you see that this is, in fact, the fundamental group of the closed orientable surface of genus G. So that's a very nice example which appears in the classification. And another example is the same but for non-orientable surfaces. So you can take the group which is generated by A1 up to AG such that the product of the squares is 1. And this group is also elementarily equivalent to F2, but now you have to assume that G is at least 4. And similarly, this is the, yeah.
If you finish your sentence, then I'll ask it.
Okay. Yeah, I wanted to say this is the fundamental group of the non-orientable surface of genus. Yeah.
My question is, if you know, from here you went from the category of abelian groups to the category of groups, and you kept the ranks. If you go from this to semigroups, does it fail? Is there any place where it's known to fail?
I think Sela now is working on semigroups.
Okay.
So you can have a look at his papers, but I
Good luck.
Yeah, good luck. Yeah. Yeah. So I know there are some works, but yeah, it's probably difficult.
Those are undecidable theory, I think.
Yeah, probably. Yes. Okay. So these are the two examples that I wanted to give you, and then I would like to. Okay. So first, maybe let me. Let me say that then Sela gave a complete classification of the finitely generated groups that are elementarily equivalent to a torsion-free hyperbolic group. So that was a few years after. Also, this one was published in. This one was a few years after. So given the torsion-free hyperbolic group. G classification of the G prime finitely generated such that G prime is elementarily equivalent to G. And so I don't want to give you the definition of a hyperbolic group. If you don't know what a hyperbolic group is, for now you can just take F2. And then in the second part of my talk, I will talk about hyperbolic group with torsion, and then you can just take SL2Z, which is a very nice group that everybody knows. It's hyperbolic, and we don't know very well its first order theory, because I mean we can conjecture that things work in the same way than for free groups, but it's not. I mean it's an open problem for now. So
just a silly question. So are these elementary classes countable or uncountable? I mean, finitely generated.
Countable.
Finitely generated on all countable.
Yeah.
And finitely presented, all of them, or they're one?
Yes. That's something I will tell you. Yeah. So so now what I would like to do. So my two goals in the talk. First, I will state Sela's classification. And you will see from the classification that the family is countable and that the groups are finitely presented. And then I will try to explain how we can generalize the classification to at least partially to hyperbolic groups with torsion. And as I said, you can just take SL2Z if you want, if you don't know hyperbolic groups. But just to motivate the question, there is a result of Sela of Gromov, which says that if you take a finitely presented group at random, in some sense at random, then it is hyperbolic. So it's a very nice class of groups. Okay, so let's start with Sela's classification. So for this, we only need two building blocks, and then from these two building blocks, we can construct all groups, of all finitely generated groups that are elementarily equivalent to F2. So the first one is just, so let's fix torsion-free hyperbolic group. Then the first operation that you can do, which preserves the theory, is just do a free product with Z. So G prime, which is G free product with Z, is elementarily equivalent to G. So you see, this is a generalization of the solution to the Tarski problem, because if you take for G F2, then for G prime you get F3. So it's a natural generalization of the solution to the original question of Tarski.
So G is non-elementary.
I should say G is not trivial and it's not Z. Yeah. Yeah, otherwise, it's not so difficult to classify the models. Okay, and then there is another operation which is a bit more difficult, which is as follows. So take an element G in G, and suppose that you can write this element as a product of commutators. So write G as, say, U1, B1, up to UL, BL, with L at least 1. So the UI, BI belong to G. And there is a technical condition, which is that the group generated by the UI and VI contains a free subgroup. So this is a technical condition. I will explain in a moment why it's important. But so this group is not too small. So in a hyperbolic group, there is a trichotomy. Either a group is finite, or it contains Z as a subgroup of finite index, or it contains F2. So we are in this situation. So if there is an element like this, then what we can do is the following. So we define G prime by, so we take G, and then we, okay, so let me first write a free product. So we take the group generated by A1, B1, up to AL, BL, and C, such that C can be written as the product of these commutators, A1, BI, B1 up to AL, BL. And then you just identify G in this factor with C in the other factor. And the result is that G and G prime are elementarily equivalent. And in fact, it's even stronger. G is elementarily embedded into G prime, which means that in the first order statements that you consider, you can allow constants from the group G. And that was the same here, in fact. Here you can also see that G is elementarily embedded into G prime. And you see the condition that the element G could be written as a product of commutators here is a necessary condition, because now in this group, if you allow constants, so if you consider this statement, you see that in this group G can be written as a product of L commutators. So if this is not the case in G, then this cannot be true. So this is a necessary condition. And in general, we illustrate this construction with a picture like that. So you draw G in a box, and then you glue on top of it a surface like that of genus L. And this is the prime. And that's what we call a floor. And you can do the same also with yeah, okay, I won't write it, but you can do the same with non-orientable surfaces. So you can, if G can be written as a product of squares, you can do exactly the same operation. You can amalgamate with a group generated by elements and identify G with the product of the same number of squares in this side. And we can also allow finitely many boundaries, but then it's a bit more difficult. Like you have G, and then you have a surface with multiple boundaries, like this. But then to describe this group, you need more than just one amalgamated product. You need H&N extensions, or you need the notion of a graph of group. So, I mean, technically it's a bit more difficult, but there is no conceptual new thing. And so the result, okay, so maybe I should give you a definition before I give you Sela's result. So the definition is the following. So you take two groups, G and a subgroup H, which are torsion-free. And so we say that G is a tower over H. A tower or a hyperbolic tower. If there exists a sequence of groups, so there exists an integer k, which is at this 0, and a sequence of groups, so G0, which is H, contained in G1, up to Gk, which is G, such that, so if you take k equals to 0, it just tells you that G is a tower over itself, which is not very interesting. In the case where G is at least 1, you assume that Gi plus 1 is obtained from Gi just by doing an operation which is 1 or 2. So you can do either a free product or you can do a surface like that. Like 1 or 2. So these are the two operations that we need. And then I can state the classification result.
And these operations will preserve torsion freeness.
Yes, yeah. Yeah, because I mean that's you can see it directly, but it's also an immediate consequence of the fact that they have the same theory. Okay, so I was saying, now using this definition, I can state the classification. So the result is the following. So you take a torsion-free hyperbolic group. And G prime, a finitely genetic group. Then G is elementarily equivalent to G prime if and only if there exist two subgroups of G and G prime. Such that H is isomorphic to H prime, and G is a tower over H, and G prime is a tower over H prime. So that's the classification.
Is this a decidable property?
Yeah, it's a decidable property. Yeah, there is an algorithm. You give it G and G prime, and it says yes or no. It's elementarily equivalent or not. And so you see, like, why do we call it a tower? It's because you just so you start with H, and then maybe you do a free product with Z, and then you do a surface, and then maybe you do another free product with Z, and you do it multiple times. And so what you get in the end is something which looks like a tower. And then, so this is G, and you have a similar picture for G prime. It's something, and so these two groups are isomorphic, so you have an isomorphism between these two groups, and yeah, that's why we call it a tower. And so you see that, I mean, this family will be countable, and this family will be countable, and in fact there is a nice corollary, which is that with the same assumptions, G prime is a hyperbolic group. So a fortiori, it is finitely presented. So this is a consequence of Sela's classification, and that's also something that I proved for hyperbolic groups with torsion like a few years ago. Okay, so that's the classification. And so in the rest of my talk, I would like to explain how
Still true? Well, which part of it?
the fact that G prime is hyperbolic.
Okay, just that, not the other part.
No, this is what I would like to try to explain in the next part of the talk. And I don't have a complete result at the moment. This is partially true, but this is completely true. Okay, so. Okay, so now what happens with torsion? Well, so as I said, if you don't know hyperbolic groups, you just take SL2Z, and in fact, it's not hard to see that the subgroup of SL2Z, which is generated by these two matrices, is a free group. And it is a subgroup of finite index, in fact, index 12. So you might think, okay, this group is almost free, so it should be easy to extend the results from the torsion-free case to this case, and it's not so easy. And yeah, for instance, there is this, I mean, if you are a model theorist, there is this well-known result that free groups are stable, and it's still an open question for SL2Z, even if it has a finite free subgroup. So it's not clear that we can deduce information about SL2Z just by knowing that it has a free subgroup of finite index. And by the way, it's a famous open problem whether every hyperbolic group has a finite index hyperbolic group without torsion. So even if we could deduce information from finite index torsion-free subgroup, we could not use it to deal with hyperbolic groups with torsion. Okay, so what I will explain is how we can adapt these two steps, and then I will show you also that there is another step, and that these three steps are what we need to classify the groups, at least partially, so I will explain. So first, there is an obvious obstruction to the first point, in this case, which is that SL2Z has a non-trivial center. Namely, the subgroup generated by minus identity. And so, in particular, it satisfies the following sentence, which is, there exists a non-trivial element such that for every y, xy is equal to yx. And it's not difficult to see that this statement will not be true anymore when you take the free product with z. Okay, so this symbol means the sentence is true in the group. Okay, so what can we do? In fact, this is not a very serious obstruction because you see, the only thing we need to do is to, when we add this letter, we can let this new letter commute with the center of SL2Z, and that solves the problem. So that's the result I proved. 19, which is that, so let G be a hyperbolic group with torsion. Possibly with torsion. And it's a well-known result that there is always a maximal finite normal subgroup. Let H be the maximal normal finite subgroup of G. Then the group G prime, which is, so you take G and you add a new letter. So if you take a free product, you just add no relation. But here, the relations that you add is that T centralizes H. And the result that I proved is that this group, in fact, is, so it's not elementarily equivalent, but it's, okay, I write it on the next board. It's AE equivalent to. By AE, I mean that I only consider statements of the form for every x there is y such that blah blah blah. And for now, I don't know how to prove that they are elementarily equivalent, because for torsion-free hyperbolic group there is a quantifier elimination result, which is due to Sela, according to which when you have a definable set in a torsion-free hyperbolic group, you can always, I mean, it's always a Boolean combination of for all exists sets, which is an open problem for hyperbolic groups with torsion. So what I was saying is that then G prime is for all exist equivalent to G. And yeah, so what I said, I should write it, is that if G and G prime are two torsion-free hyperbolic groups, then it's a result of Sela that G and G prime are for all exist equivalent if and only if they are elementarily equivalent. That's a very, very deep result, quantifier elimination result, and this is open for hyperbolic groups with torsion. So that's the main obstruction, in fact, if you want to really understand the theory. So that's why I said what I'm explaining now is just a partial result, because I can only deal with AE theories. I will never be able to deal with the complete theory until we have the quantifier elimination with torsion, which is very far from.
Do you still get an elementary embedding of G into G?
Yeah. No, I mean
elementary AE elementary.
Yeah. Yeah, this is true. I can allow constants from G. Yeah. And in fact, I should say that then in a paper with Jonathan Fruchter, who is here, we proved that this result is in fact true in a context which is much broader. We prove that this is still true, the statement here is still true, if G is asymmetrically hyperbolic. So, so the class of asymmetrically hyperbolic groups is a very large class of groups. For instance, Montse talked about rags, and rags, when they are not directly decomposable, they are asymmetrically hyperbolic. Also, Gianluca mentioned some results on Artin groups, and there are lots of Artin groups that are asymmetrically hyperbolic. So there are lots of groups that are not hyperbolic, but they are asymmetrically hyperbolic, and still we can use the same techniques to prove results on the first order theory. And that's how also we deduce that these groups have positive trivial positive theory. That was a result mentioned in Monce's talk. So this is true in a much broader context. And in fact, what we need to state the classification is not this result, but a result which is just a bit more general, which is the following. So you take G, a hyperbolic group, and you take H, a finite subgroup, such that the normalizer of H in G is big. So it contains F2, so it's very big. Then you can add a new letter centralizing H. So the thing is that I have to define another finite subgroup H prime. So let H prime be the maximal finite subgroup of G, which is normalized by the normalizer of H. Then, if we add a new letter centralizing this H prime, it preserves the AE theory. You see, it's a generalization of this result where we take in that case, H is just normal in G. Here it's a bit more general because the normalizer of H is maybe not the whole group, but still, if it's big enough, we can prove the same result. So that's how we deal with the first obstruction. So now I would like to talk about the obstructions to the second point, which is in fact a much more serious obstruction. So in fact, this obstruction was overlooked in previous works on similar problems. And so I thought it would be easy to extend the result, like to generalize the point 2 with torsion. And in fact, it turns out that this is by far the main, the most challenging obstruction. So before I explain what is the obstruction, I would like just to say a few words about how it works for hyperbolic groups without torsion. So let G be a hyperbolic group, and let G be a commutator in G. With UV in G, and I assume that the group generated by UV is big, so it contains F2. So it's a technical condition. It's not really important to follow what I'm saying, but and then define as before the group G prime, which is just an amalgam of G with a free group AB, and you identify G with the commutator here. So it's always the same picture. You have a box with G, and then you glue a tower, and you identify the boundary element with G. So G is AB. So first, what I would like to explain is when G is torsion-free, how do we prove that these groups have the same theory? So, how do we prove that G is elementarily equivalent to G prime if G is torsion-free. Okay, so this is too ambitious, so I will only explain a very basic case. So let's say baby case, which is the existential theory. So how do we prove that G and G prime have the same existential theory? Which means that you have a system of equations and inequations. You have a solution in G. How do you get a solution in G prime, and vice versa? There is one sense which is obvious, which is this one. Because G is a subgroup of G prime, so if you have a solution to an equation or an inequation in G, then you have it automatically in G prime. So this is obvious. So the difficult point is how do you prove the other direction? If you have an existential statement in G prime, how do you get an existential statement in G? So the idea is the following. So with this picture, there is a natural morphism from G prime to G, which is a retraction, so I'll call it R, which is defined by mapping A to U, B to V, and it's the identity on G. And on G, it's just the identity. So you see it's a well-defined morphism because G can be written as UV in G. And so now the idea to prove that you have the other inclusion, that an existential statement in G prime is true in G, is to find complicated automorphisms of the group G prime, such that when you precompose this morphism, you get morphisms that are injective on balls that are arbitrarily large. So I'll write it on the next board. Okay, so what I was saying is that you can always, in the torsion-free case, you can always find, so that's the idea, you can find a complicated sequence of automorphisms of the free group generated by AB. Such that when you precompose your morphism R by sigma n, so I'll call it Rn, this morphism is injective on finite balls that are arbitrarily large. Such that this morphism is injective on arbitrarily large finite subsets. So that's something you can do. It's not so difficult, or it's not obvious, but... And so then you deduce that if you have an equation or an inequation in G prime, so this is a word and this is a tuple of elements of G prime. So obviously when you apply a morphism, equations are always preserved. So this will be true, of course, in G for any n. But now if this is an inequation, it's more difficult, but you know that this element belongs to some big ball, and then when you take n large enough, you preserve this inequality. So that's how we prove the other inclusion. And now the problem is that morphisms from free groups or from surface groups to hyperbolic groups when there is torsion are much more difficult. So let me give you an example. So an example showing that this strategy cannot work when the target group has torsion. So first, let me give you a definition. So an element X in a free group is called primitive if it is part of a free basis. Primitive if it belongs to a free basis of Fn. And I divide by P the set of primitive elements. Primitive elements. And so the point here is that there exists, so this is a fact, there exists a morphism phi from a free group of rank 2 to a hyperbolic group with torsion. Which is in fact linear. I mean, that will be important for some remarks that I will make, such that the image of this morphism is big, so the image contains F2. So you see, this assumption that the image contains F2 in the previous case was used because you have enough room to find the automorphisms, so that's an important assumption. But every primitive element is mapped to an element of order at most n. So there is a morphism, and also there exists an integer n, such that for every primitive element, this is trivial. Okay, so why is it a problem? Because now using this morphism, I can construct a pathological tower like that. So now, using this morphism, define G prime, which is just, so I take this group G, I put it at the bottom, and then I glue a torus, and I identify the boundary of the torus, which is AB. So this is the group generated by AB. I identify the boundary with the image of the commutator in my group. So I identify this group with the image of AB. And here there is still a natural morphism R from G prime to G, which is just an extension of phi. So it maps A to phi of A, B to phi of B, and on G it's just the identity. And so you see now, the problem with this morphism is that it kills every primitive element. So there is no way you can precompose this morphism to get an injective sequence. Like for every automorphism of your free group, and for every primitive element, because you see this set is preserved in the automorphisms of the group. So for every such things, you have this. So it is impossible to precompose this morphism to get morphisms that are injective on balls that are as large as you want. So you see, this is a serious obstruction, and that's in fact the main. I mean, it took me a lot of time to solve this problem. And in fact, just by the way, it's related to nice open questions. So one is more a conjecture than a question. It's due, I think, to Zelmanov. Which is that the conjecture is that if you have a morphism from Fn with n at least 3, because this for F2 this would be a counterexample to the conjecture, to a linear group GLMC. Such that the image of any primitive element has finite order, then the conjecture is that the image is small. So what it's small in some sense, which is that it should be virtually solvable. What?
What's the?
Sorry, it's the set of primitive elements. Okay. Then the image, conjecturally, is virtually solvable. And the morphism I gave you here is a counterexample when n is 2. But when n is 3, it's you see, it's in principle it's very different. But in fact, that's not really, I mean, in this context, that's not really the natural generalization, because here there is a coincidence, which is that the automorphism group of F2 is the same as the mapping class group of the punctured torus. But when the genus is larger, then it's a smaller group, which is the mapping class group of the surface. So there is another question, another interesting open question, which is the following. So the second question is, so now instead of taking a fruit group, you take the fundamental group of a surface group. And so the question is, does there exist a morphism phi from the fundamental group of the closed surface of genus at least 2 to a hyperbolic group such that, so it's more or less the same question, such that the image contains F2, so the image is big, but so now the analog of the primitive elements is the set of simple closed curve, which is also preserved by the automorphism group of this group, such that phi of x to the n, so I mean, okay, phi of x has finite order for every simple closed curve x. And for the torus with one boundary, this is exactly the same. The set of simple closed curve is the same as the set of primitive elements. So you see this the only case where the two questions are the same. And so, yeah, surprisingly, the answer is yes when G is 2. but it's open for G, small g, but open for G greater than 3. And surprisingly, the answer is also yes, so it's very different from the first question. It's also yes when you take GLM2C, GLMC instead of G at the target. Yes if G is replaced by GLMC at the target.
For all little g. All.
Yes, for any G at least 2. And so the only construction I know uses what is called the topological quantum field theory, which I don't know, but it's in a paper by Coberda, who was here, he's not here anymore, and Santaruban. So you can find such construction in the paper by Coberda and Santaruban. So you see, if I come back to my classification, the generalization of the second point, of the second building block, is much more difficult because of this kind of weird morphisms from free groups or surface groups to hyperbolic groups with very pathological behavior that do not appear when your target group is a torsion-free group. So I won't give you a precise statement, but the idea is that what I can prove is that, so let's say it's 2025, it's not yet on the archive, but soon. So if you take a hyperbolic group, and you define G prime as above, so you take an element which is a product of commutators in your group G, and then you amalgamate with the surface. So it's always the same picture. And as I said, it comes with a natural retraction mapping because your element can be written as a commutator here. There is a natural retraction. And the idea is that if this morphism is sufficiently complicated, then they still have the same first order theory. With two quantifiers. If R is, so I don't want to say exactly what I mean by sufficiently complicated, but sufficiently complicated means that complicated enough to overcome these weird morphisms that appear in this context. Then G and G prime are for all exist equivalent. And just one remark is that this, it has to be sufficiently complicated, but also it has to be a first order condition. Like in the torsion-free case, the condition is that the image is non-abelian, which is very easy to express. You just say that the generators do not commute. Here, the condition has to be first order, which is in fact the most challenging thing because like when you try to find a solution, in general, it will not be first order expressible. So that's somehow the main problem. So then I explain how to generalize these two constructions, 1 and 2. And then I don't have time, but there is a third thing that could happen, which is a bit of a different nature. But then with these three constructions, you can get all the finitely generated groups with the same AE theory as a hyperbolic group with torsion. And then, as I said, the ultimate goal would be to eliminate quantifiers to prove that it's still true for the whole theory. But this is, this is not for now. So I think it's good to stop.